Okay, we're talking about the rider on the beam. And the first question I asked was, what's a unit vector in the direction of motion of the rider at this position, where the I and J vectors are here? Now, the very obvious answer, but nobody really got it. So that concerns me a little bit, so you're going to have to give this some thought. Make sure you understand this. That unit vector in the direction of velocity of the rider is the J vector. I mean, the direction of the velocity is here. Now, people were saying this direction, that direction. We're going around a circle. At this instant, you're moving in this direction, okay? You're moving in the vertical direction. Now, very shortly after, you're going to be back this way and then back this way. You're always going to be tangent to the circle. Tangent to the circle at this point is vertical. And the vertical unit vector is J, so you don't have to do any calculations. That's it. Okay, so the J vector is, and I don't know if I wrote that down, the J vector is the unit vector in the direction of motion. And that means that if you can figure out the speed of the rider, then you know what the vector velocity of the rider is. They're moving into Chapter 3, where we have motion in a plane. And this is one of the important examples of motion in the plane. And we're doing it, of course, in the context of our rider. Okay, so question now, if the angular velocity is 2 radians per second, how fast is the rider moving? Well, that's very clear. A radian means the distance of 1 radius along the arc. If we're moving at 2 radians per second, it means distance of 2 radians along the arc every second. So we're moving at 2 radial distances per second. Radius is 30 centimeters, so that's 60 centimeters per second. So that's the speed of the rider. The velocity of the rider is the speed times a unit vector. Okay, any vector is equal to its magnitude times a unit vector in its direction. Okay, so the speed times a unit vector in the direction, 60 meters per second times J. So there we have the velocity vector for the rider. The speed, 60 centimeters per second. Velocity has a direction, 60 centimeters per second times J. Okay, now, after 4 seconds, what's the angular position? Well, 4 seconds, the angular position at 2 radians per second is 8 radians, assuming this is your t equals 0 position. So starting from your t equals 0 position, you go all the way around, which is a little over 6 radians, and you still got a couple of radians to go. Now, actually got a little less than 2 radians to go, because around the first revolution, the first rotation, you go a little more than 6 radians. So you got a little less than 2 radians here. Look about like this. Maybe even a little closer to the y-axis. Now, what's our vector position? The vector position here, well, the y-coordinate of this point, you have 30 centimeters here. So it's 30 centimeters times the sine of theta. Theta being your angle, being your 8 minus 2 pi. Notice I didn't write radians here, because if you don't write degrees or rotations or grads or whatever unit you're using, it's automatically radians. That's because you do calculus with angles in radians. You can do it with angles other than radians, but it's messy. You can have conversion factors. It's confusing. So we do calculus with angles in radians, and we do calculus in this course. Okay, so y is 30 centimeters times the sine of 8 minus 2 pi. So you got 8 radians, and okay, I use 8 minus 2 pi. I wrote down 8 radians is coterminal with theta equals 8 minus 2 pi radians. So, yeah, your coterminal angle, your angle from the x-axis over to here, is your 8 radians that you have from the whole rotation plus, or just theta equals 8 minus 2 pi radians. Should have said that earlier. Okay, hopefully that clarifies it. So anyhow, that's your y-coordinate, and here's your x-coordinate. 30 centimeters times the cosine of 8 minus 2 pi. Incidentally, you could write 30 centimeters times the sine of 8. Now, engineers are famous for writing down angles without degrees, so that might look like 8 degrees to you. Okay, and even in math courses, people do that. But sine of 8 is sine of 8 radians, not sine of 8 degrees. That's what it means. If you try to do calculus and you think it's, it really is 8 degrees, and you try to do calculus with it, you're gonna fail miserably on that calculation or that symbol or whatever. Okay. You need to know these. You need to know the trigonometry, and I can't take the time to teach you the trigonometry here. Okay, so there's your y-coordinate, there's your x-coordinate, all of which you should know from pre-calculus. And if you don't, you're kind of responsible for making sure that you remedy that. If you want references, let me know. Okay. Now this gives us our r vector. Now if you've done the homework for today, which a lot of people didn't for some reason, even people have been doing it regularly, you have a vector that we often refer to as the r vector. That'd be the vector from here to here. So if I want to make that a vector, I call this an r vector. The big R stands for our rider. It doesn't stand for radians or anything else. It stands for our rider. It looks almost like a gamma, so make a better R. Here's our r vector. Okay, and that's our r vector at 4 seconds. That r vector, and I could write this as r of 4 seconds equals the magnitude of 30 centimeters times the sine of theta times the j vector. So here's that vector. Here's 30 meters per second times the sine of 8 pi, 8 minus 2 pi, and here's a vector that represents that displacement from the origin. And here's a vector that represents 30 centimeters times the cosine of 8 minus 2 pi, the vector from the origin out to that point. If you add these two vectors, you get the r vector. And here we have it. Well, you need that, and you're going to need a little more that I'll try to give you a little more guidance on in the assignment that I've already sort of posted, but I'm going to have to throw in a little more guidance because y'all are going to need a little more help in understanding the vectors. And I say that even though people did well on the vectors in the Mastering Physics assignments, it's not quite there yet. So we'll work on it. And sorry for being a little incoherent. I should have eaten lunch an hour ago, so I better go do that.